So we've already done a section on work and kinetic energy, and we're going to add to that a little bit by talking about potential energy and power. We're going to start by just working through a pretty simple example, well, maybe not simple, but fairly straightforward example that covers some of the things we talked about under work and kinetic energy in the last section. So we're going to look at this box, and it's sitting on rollers, and it's being pushed by this force F. It's F applied, but I'll probably just call it F when I get to some drawings here. It's 120 newtons. The box is 30 kilograms. There's a friction force that's about 5 newtons. The box moves a distance horizontally. Notice in the direction of the applied force and opposite direction of the friction force of D equals 0.8 meters. There are two other forces, the force of gravity pulling down on it with a lowercase w, and the normal force pushing up on it that's called N. I'll probably call this one F sub g, force of gravity. It's the same thing by a different name, and I'll probably call this F sub n when I'm drawing it. And so we're going to answer some questions. We're going to say, what's the work done by each of these forces? Right? And you should have some quick answers to that, actually, at least in some of the cases, like for these two guys. And then we say, what's the net work done on the box? So we figured out what each of the work of each force has done in this question, and then we're going to figure out what's the net or total work done. Then we're going to say, what's the change in kinetic energy of the box? And finally, we're going to say, if the box started from rest, what was its final speed? So let me switch over here and draw a picture that looks like what we just had there. I won't draw the rollers out, but I'll have a box here, and it's going in this direction, and it travels a distance of d equals 0.8 meters. It's got a force going this way. That's F, it's 120 newtons. I'll draw this lowercase f. This one is 5 newtons. And then it's got a weight, which I'll call force of gravity. They use a W. I don't want to use a W because the W looks like the work variable. And then I'll say there's a normal force pushing up. We've already talked about why that's there. And finally, I'll say the mass of the box is 30 kilograms. All right, maybe 65 pounds or so. And now the question was, what's the work done by each of the forces, right? And so if you remember your formula for work is equal to force times distance. In the case of the first force, it's 120 newtons, right, times 0.8 meters, and that's 96 newton meters, or 96 joules. Right, if you do your math right. Notice it's positive because the box is moving in the direction the force is pushing. Right, so this is for our push force. And now let's look at the friction force, right? Maybe I'll put a little subscript f here, and then I'll put a lowercase f there, if you can tell those apart. And so this is, now we've got my friction force, which is pushing this way, my distance, which is pushing the other way. And so if you remember, I have to put a minus sign there. If the box moves opposite the direction of the force, the work is negative, and so in this case it becomes negative 5 newtons times 0.8 meters, which is about minus 4 newton meters, or minus 4 joules. And so that's the work done by this force, right, and this force. And now we can ask the question, well, what's the work done by gravity and the normal force? And you should probably be able to do this in your head, because if you remember, the work is the force times the distance moved. I'm pausing for you to think about that for a second. In the direction of the force, right? This is if it's opposite direction of the force. But here, for these two guys, the distance moved is perpendicular to the direction of the force. And so since the work done by the force of gravity is equal to the force of gravity times the distance moved in the same direction vertically. This is equal to 0 because it moves horizontally. It neither moves a little up nor a little down even. It's just 0. Similarly, the work done by the normal force is equal to 0 because the normal force is perpendicular to the distance, just like the force of gravity is perpendicular to the distance it moves. And so that means both of those works at 0. And so now we can say, look, the network is the sum of all the works, right? It's 96 joules plus -4 joules plus 0 joules plus 0 joules, which is 92 joules. So that's the net work done. If you go back and look, the subsequent question is, what's the change in kinetic energy of the box? Right? We've already said in previous discussions, as the box moves, it accelerates, it speeds up. Remember, kinetic energy is 1/2 mv squared. And so as it speeds up, its velocity increases, and that causes its kinetic energy to go up. Right? It turns out, if you remember from last time, the net work done is equal to the change in kinetic energy, and we've already determined what the net work done is 92 joules. And so the net work done, the change in kinetic energy of the box is 92 joules. Now if I go back one more time here and read the last question, it says if it started from rest, what's its final speed? Right? Well, now we've got to somehow relate that kinetic energy that it's gained to the speed of the box. And if you remember, the change in kinetic energy is Ke final, which we call Ke2, minus Ke1. But if the box started from rest, right, this guy is 0, because we already said kinetic energy is 1/2 mv squared, and v is 0. The whole thing is 0. And this just says that then the final kinetic energy is equal to the change in kinetic energy of the box, or I guess I'll write it up here, Ke2 is equal to 1/2 mv2 squared is 92 joules. Is that in? It is. Right? And so now I can just take this piece of this and try to solve it. If I write 1/2, well, that wasn't very good. 1/2 mv2 squared is equal to 92 joules, right? Then I can multiply both sides by 2, and the 2's cancel. I get m v2 squared is equal to 184 joules. Just multiplied 92 by 2. And then I can divide both sides by the m, which is 30 kilograms. And this gives me v2 squared, right? The m's cancel. I could plug in the hundreds if I wanted to, but I don't need to. They just cancel. This gives me about 6.13 joules per kilogram. We could go all the way back and figure out that a joule is a kilogram meter squared per second squared, and so joule per kilogram is a meter squared over second squared. And so when I take the square root of that, meter squared over second squared, I get about 2.4 something. I'll say 4.7. Don't hold me to it. It's less than 2.5 V2. Right. And so when he's acted on by this series of forces over a distance of 0.8 meters, that's what his speed is at the end. So this is sort of a review of kind of what we covered last time, but it's a little bit about work and kinetic energy and which forces are doing what work. All right, let's go back to this one. So let's talk about gravity doing work. This is where this concept of potential energy that I talked about when I read the title of this section a few screens back comes from. It turns out that when an object is dropped, gravity acts on the object with a force of mg. We've already talked about this in our Newton section. If the object falls from a height h, then the work done on the object by gravity is just the force times the distance. It's the force of gravity times how high it was, right? It was a height h. And once again, if it's falling, the force and the distance are in the same direction. And so the work done is positive. It's the force of gravity is just m times g. We've already done that. And so the work done by gravity is this mgh here. We know that the change in kinetic energy of an object is equal to the work done. And so that means the change in kinetic energy for a dropped object is just mgh. And so we could say mgh is our change in kinetic energy, which is 1/2 mv2 squared minus 1/2 mv1 squared. But if it's dropped from rest, then this guy is 0. And we just get mgh is equal to 1/2 mv squared, mv2 squared, our final velocity squared. And so this kind of relates the final velocity the object gets, or the final kinetic energy, the whole thing, to how high it was dropped from. And so you can kind of have the idea of any time you hold something up in the air, you can just release it, and right before it gets to the ground, it has this much kinetic energy. And so putting things up high under gravity is kind of like storing energy in them, because I can just multiply that mgh, push the thing off, and I can turn that all into kinetic energy and get that whenever I want. So this leads to the concept of potential energy. We say potential energy is the energy stored in an object due to its position or configuration. For gravity, the potential energy is stored due to its position. How high up is it above whatever it's going to land on determines how much potential energy it has, how much work gravity would end up doing on it. Objects placed high above the ground have this potential energy because if they're dropped from that position, gravity is guaranteed to do work on them, and they'll gain that energy as they fall, mg times h. And so if an object falls from a height h above the ground, gravity does work equal force times distance, or mgh, by the time it reaches the ground. So we define the object's potential energy near the Earth's surface. This is stuff we're just, within a mile or two of the Earth's surface, as m times g times h. That's its potential energy. This is the amount of work gravity would do on it before it reaches the ground, if we're dropped. So now we can do just a quick example of calculating the potential energy of something. What's the potential energy of a 100-kilogram boulder sitting on the edge of an embankment that's 15 meters high? Right, well, the potential energy is just m times g times h. It's 100 kilograms times 10 meters per second squared times that h, which is 15 meters. That comes out to 15,000 kilogram meters squared over second squared if you multiply all the units out. And that's just 15,000 joules. Once it's on the ground, it has a potential energy of 0 joules. So when we go back to our work is equal to change in kinetic energy equation, we've got an extra term in there. We've got this potential energy term over here on the right. The work now no longer includes the work done by gravity because we've included it over here in this potential energy term. And so now we say the work done by forces other than gravity is the change in kinetic energy plus the change in potential energy. If there are no other forces acting other than gravity, then that W is just 0, like if we drop something and neglect air resistance, right? Then the change in kinetic energy plus the change in potential energy is equal to 0. We can rearrange this a little bit and write Ke2 minus Ke1 plus Pe2 minus Pe1, because those are the definitions of the change in potential and kinetic energy. And if we wanted to, we could go all the way through and plug in the equations for what is the final kinetic energy, Ke2, and initial kinetic energy. Hang on one second, I have a little mistake there. There we go. So then we can write it as 1 half mv2 squared minus 1 half mv1 squared plus mgh2 minus mgh1 instead of this way. If we go back to this version, we can put the 2's on one side and the 1's on the other, just by rearranging. Again, all this is equal to 0. Or we can write it as mgh2 plus 1 half mv2 squared is equal to mgh1 plus 1 half mv1 squared. What these equations are all saying is that the final kinetic plus the final potential equals the initial kinetic plus the initial potential. This is a statement of conservation of energy. This is saying that if I start out with a certain amount of potential energy plus kinetic energy, then whatever I have at the end has to be equal, provided I did no other work on my system. My system didn't gain or lose any other energy. This becomes a statement of what we call conservation of mechanical energy, or just conservation of energy. It's saying the energy at the beginning is equal to the energy at the end if I'm not doing any other work on it, on my system. So if we drop the ball from a height h, it starts with a potential energy 1 is equal to mgh, and a kinetic energy equal to 0 because we dropped it from rest. Just before it hits the ground, it's got no potential energy, Pe2 equals 0, because it's at the ground, essentially. And it's got all kinetic energy. This should be Ke2. And now it is. So the final kinetic energy is 1 half mv2 squared. That's going to be equal to the initial potential energy. In other words, all this potential energy that it started out with has to get turned into kinetic energy that it ends up with. The energy is conserved. It just moves from the potential energy bucket to the kinetic energy bucket. There it is again. Now, so we can do a simple example of this. We can say potential energy stored in an object due to its position or configuration. What is the potential energy of a 100 kilogram boulder sitting on an embankment that's 15 meters high? In fact, we already did this. We multiply 100 kilograms by 10 meters per second squared by 15 meters, and we got 15,000 kilogram meters squared over second squared, which is 15,000 joules. If the boulder falls off the embankment to the ground below, what would its kinetic energy be just before it hit the ground? Right. And so we can address this question here. Let's see if I can draw a picture of it. There we go. So here's my boulder, right? It's just getting pushed off this embankment. Its initial height is 15 meters. Its mass is 100 kilograms, right? And so PE1 plus KE1 equals PE2 plus KE2. All right, this is mgh1 plus 1 half m v1 squared is equal to mgh2 plus 1 half m v2 squared. Right, since it starts essentially from rest, we can get rid of this guy and say that one's 0. H2 is right before it hits the ground. We're going to say H2 is equal to 0, or as arbitrarily close to 0 as I want to get. And so that gives me these two. That gives me mgh1 is equal to 1 half m v2 squared. Now, if I wanted to, I could calculate what the kinetic potential energy is beforehand. In fact, I had 15,000 joules, but I could also do just a tiny bit of algebra here if I wanted to, and I can cancel the m's. Multiply by both sides by 2, and I get 2gh1 is equal to v2 squared, or v2 is the square root of 2gh1. h1, which is the square root of 2 times 10 meters per second squared times 15 meters. 2 times 10 is 20, times 15 is 300. Square root of 300 is about 17.3 meters per second. That's how fast it's going here at that spot. So the potential energy, which is all it has up here, gets turned into kinetic energy, which is all it has down here. So I can ask a few questions. I can say, getting back to our first example, a car's going down the highway at a constant speed. Identify 4 forces acting on the car, including air resistance. So you should be able to do that. Look at that box problem at the beginning and tell whether the work due to each of those forces is positive, negative, or 0. In the second problem, a 0.3 kilogram ball is dropped from 20 meters high. What is its initial potential energy? Right? You should have a formula for that. What's its initial kinetic energy? Assume it's dropped from rest. What are the final potential and kinetic energies just before it hits the ground? Right? You should be able to follow the calculation we did just a few minutes ago and work your way through that. Okay, new topic, power. So this one you might be a little more familiar with, although you should be a little familiar with energy. Power is the rate at which energy is either produced or consumed, depending on the context. It's also the rate at which work is being done. So it just depends on the context for which one of those powers you're talking about. So you might see power written this way. P is equal to change in work over change in time. It's kind of like a car's power is sort of written this way often. Or power is equal to change in energy with respect to time, right? The rate at which energy is produced or consumed. The dimensions of power is energy over time, but energy has dimensions of mass times length squared over time squared. We've kind of been through this already. But to get to power, I have to take those energy dimensions and divide it by time, and that means dimensions of power are mass times length squared over time cubed. So those are dimensions for power. The SI unit, or when I was a kid we called it the metric system, but the SI, the International System of Units for Power, are joules per second, also known as a watt. So if you have like 30 watt speakers, it means they consume 30 watts of power. If the power consumption of a light bulb is 100 watts, that means it consumes 100 joules every second. The sun delivers about 4 times 10 to the 26th watts. This means that the sun releases about 4 times 10 to the 26 joules of power, of energy every second. A joule, so 4 times 10 to the 26 is 4 with 26 zeros after it. And so the sun is a great energy source. The sun releases zillions of times more energy per second than we consume. So the sun is a good source of energy for us if we can harness it pretty well. Or to put that differently, if the sun burns out, we've got to go down to Lowe's and find a light bulb that has 4 times 10 to the 26 watts on it. I think that's in aisle 17. So a few examples of power. If a car goes from rest to 30 meters per second in 5 seconds, how much power did that require? Right? Well, remember, power is work over time. Work is the change in kinetic energy. And so if it goes from rest to 30 meters per second, its kinetic energy is changing. Right? It starts out with no kinetic energy since it was at rest, and it ends with 1/2 mv squared of kinetic energy, or 1/2 times 1,000 kilograms times 30 meters per second squared. You can neglect that little square bracket there. That comes out to 450,000 joules of kinetic energy. So it went from 0 kinetic energy to 450,000 joules of kinetic energy in 5 seconds. And so the power is the change in energy over the change in time. That's 450,000 joules divided by 5 seconds, or 90,000 joules per second, or 90,000 watts. That was the power required to do that. You should keep in mind that if you're talking about a car's power, that's not actually the total energy used by your car, because not all of the power produced by your engine goes into moving the car forward. A lot of it goes into heat and stuff like that, friction, all kinds of different things. So this is just the kinetic, the rate at which kinetic energy is gained by the car. Here's another example. A light bulb needs 100 watts of electrical power to operate. How much energy does it consume in 1 minute? Right? Well, if power is energy over time, then energy is power times time. If I rearrange that, it means 100 watts times 60 seconds, or 100 joules per second times 60 seconds, or 6,000 joules. So this is how much energy that 100-watt light bulb uses in 1 minute.